In this lecture, we'll continue our discussion of the properties of stars and as they relate to the presence of biology on surrounding planets. Different stars have different habitable zones, so the habitable zone shrinks or expands based on the mass and therefore the luminosity of the stars. And so here we see the differences between a sun-like star, or G-spectral type, where the habitable zone, the green zone, includes the Earth, and no other terrestrial planet is in the habitable zone, although two are close. Hotter stars, where the amount of radiation from the star is larger, so the habitable zone is further out, and that habitable zone is also physically larger in range of distance, and it may or may not include exoplanets. For cooler stars, the habitable zone shrinks towards the star, and actually the real estate or the range of radii covered by the habitable zone is less. It turns out, however, that smaller real estate of a habitable zone of a low-mass star is overwhelmed by the much larger number of low-mass stars. So the total habitable real estate in the Milky Way galaxy is actually dominated by this type of star rather than stars like the Sun. The key parameter of a star is, of course, its luminosity. It's the energy from the star that gives rise to life in the first place. And in simple terms, this is measured in joules per second, or watts, in the metric units. It's the total amount of energy radiated in all directions in space. And as we know, this luminosity derives from nuclear reactions. During each fusion reaction in a star like the Sun, or any other star that is creating energy in this way, the energy comes out in the form of fusion. And photons are generated at extremely high temperatures and pressures. In the Sun, they come from essentially the inner quarter in radius terms of the Sun at temperatures of more than 10 Kelvin. Those photons don't move straight out through the star. At those temperatures, those are X-ray photons. They diffuse out through the star in a random walk process that takes tens of thousands of years. So it actually takes a long time for the radiation or the light from the center of the Sun to reach the surface of the Sun, after which it travels freely through space and takes 8 minutes to reach the Earth. So these photons are essentially degraded in energy from the stellar core, where they're produced at very high temperatures, and so very short wavelengths, or X-rays, to the visible light that we see from the edge of the Sun that reaches us. The luminosity is still the total amount of energy carried away in photons per second from the Sun or any star in all directions. This is the luminosity, and luminosity, as we have seen, is related to mass, because stars with high mass have much larger self-gravity and so can create higher temperatures and pressures in their interiors. They can also generate heavier elements than low-mass stars. And since this is an essential part of the story of life, even though high-mass stars are unlikely to be hosts for life because of their short lifetimes, they've been essential in putting into place the ingredients for life in terms of heavy elements spat out into space to become part of new stars. So for example, the carbon, nitrogen, and oxygen in our bodies and on the Earth was produced mostly from stars that were much higher mass than the Sun, that ejected those elements out into space, where they became part of the solar nebula 4.5 billion years ago. This difference in luminosity between a high and a low mass stars means there is more energy hitting any particular patch of the surface of an exoplanet at a particular distance from distant stars. This calculation is done using models of stellar luminosity and then the inverse square law to work out how the radiation flux at the surface of a planet depends on distance from the star. And this leads to the standard definition of a habitable zone. A planet with an orbit inside the habitable zone around a Sun-like star would be too close to a massive star for liquid water to exist. And this same planet would be on the outer edge of the habitable zone around a less massive star. Dwarf stars are important in the discussion of astrobiology because for most of the decade after exoplanets were discovered, people naturally concentrated on looking for planets around Sun-like stars because that's our situation. That's where we know a planet exists with life on it. It was only after a decade or so, when the number of planets grew, that astronomers recognized the opportunity provided by the very large number of M-dwarf stars and the fact that their cosmic real estate for habitability and planets was large. And so surveys of dwarf stars, red dwarf stars for exoplanets, are a relatively recent thing, but they're considered very important in telling the full story of exoplanets and potentially of biology in the universe. As I mentioned, the very large number of M-dwarfs, 100 for every star like the Sun, overwhelms the fact that their individual habitable real estate is less because it's a skinnier habitable zone closer to the parent star. We also don't know how often planets form at different distances from different types of stars. So this calculation has to make some assumption of a roughly uniform distribution of planets with distance from their stars. Either way, we're faced with expanding our definition of the habitable zone, this Goldilocks idea that it's a distance from a star where liquid water on the surface of a planet with no atmosphere is between 0 and 100 degree Kelvin. The particular aspect of the habitable zone that we have to relax in our definition is the outer bound, because we know that the cryogenic biosphere is an important concept, because we know there are extra heating sources that apply on exoplanets that move the outer edge of the habitable zone outwards. And so while water would be frozen in the cryogenic biosphere on a simplistic calculation, there may be reasons why that water could be liquid. This concept, the cryogenic biosphere, is really important for astrobiology now. We've seen a couple of examples. The internal heating of a geologically active planet adds heat to that planet. The presence of greenhouse gases in the atmosphere of that planet raise the temperature on the surface above what you would naively calculate based on the radiation from the star. And both of those things extend the biosphere outward. A second thing coming from our study of the solar system is the awareness that there are a dozen moons of giant planets that are very likely to have liquid water under their surfaces. So as soon as you go beyond the requirement that the water be on the surface of a planet or a moon, you have a much larger amount of real estate in play. Think of it. In the solar system, we have one water world, the Earth, one planet with water liquid in the classic Goldilocks zone. But we have a dozen, or 10 times more roughly, of places where there's liquid water, and they're almost all in the cryogenic biosphere, far from the Sun, 5 or 10 times further typically at the orbits of Jupiter and Saturn. So this is a basis for being more generous in our calculations. And yet we don't know how to do so in a systematic and thorough way because our models of biology and of exoplanets themselves are too primitive. We could even bring the biological piece into play by asking whether biological organisms could exist in liquids that exist below the freezing point of water. There are hydrocarbons, for example, that remain liquid far below the freezing point of water. So people have speculated about weird forms of life, they would not be standard biology the way we know it, in the hydrocarbon liquid lakes on Titan, where the temperature is far lower than the freezing point of water. This is a fascinating speculation, and astrobiologists like to speculate about weird forms of life, but it shows that we mustn't be too narrow in our thinking if we're to understand life in the universe. So we've seen that we need to expand our thinking on the traditional habitable zone. We have stars that have very different lifetimes when they have very different masses. And even ruling out the more massive stars as living too short a time to be interesting for biology, we're left with a very large amount of M-dwarf stars, 100 times those of Sun-like stars, where biology could exist in habitable zones that are close to those stars. More importantly, the traditional version of the habitable zone is naive and simplistic, and almost certainly wrong, especially at the outer bound of the habitable zone, because there are mechanisms, such as the internal heating of an exoplanet or the greenhouse effect of gases in its atmosphere, that can raise the surface temperature beyond which we would simplistically calculate. We also have the examples in our solar system where there's very likely to be liquid water kept liquid very far from the Sun at distances of 5, 10, 20 AU by interior heating and pressure from rock and ice on top. So the cryogenic biosphere opens up the potential real estate for biology in the universe enormously, and in a way we don't yet fully understand.